Hello class. Last time I saw you we were doing diffraction gratings, so I'm going to quickly go back through that and then move on to the new material. So before we start, let's do a start activity. You've got 3 minutes to do this task, so off you go. Okay, so hopefully you've all managed these questions. To do the first question, what you need to do is use the fact that frequency and time period are inverse of each other, and just do 1 divided by 0.33, and that should give you an answer of 3 Hertz, which remember means 3 waves per second. For the second question, we're going to be looking at the C equals F lambda equation, the one that relates wave speed, frequency, and wavelength. You want to rearrange that to make wavelength the subject, and then input the values that you have, and you should get a wavelength of 0.25 meters. Okay, then move on. Objectives for today are on the board. We're going to be looking at displacement, coherence, path difference, phase difference, superposition, and then if we get onto it, we're going to be looking at the industrial applications of diffraction gratings, which are for emission spectra and identifying gases. So, as a reminder, diffraction is a characteristic of waves, and it's a tendency to spread out. We have already seen the wave generator, and we've displayed that information visually. So this is just a recap of that. Remember, we like to think of the wave as having a wave front, and the wave front travels perpendicular to the actual direction of the wave. Perpendicular meaning at an angle of 90 degrees. This is the wave generator that we saw previously, and we talked about how the wave is able to curve around the edges of any gratings that you add on to the ripple tank. We also mentioned that there is a complicated principle behind this, and it was the Huygens principle, which you don't need to know specifically for the BTec Applied Science course. It is a nice visual aid to help you understand what's happening. The wave that you see is basically a summary of lots and lots of very, very small waves all added up to look like one larger wave. When we used the ripple tank, we saw lots of superposition. We saw sections of light and sections of dark, and we saw them alternating along the ripple tank. Now, we talked about what caused that, and we discussed the idea of superposition being constructive and destructive, and the idea of interference and what an interference pattern is. So to remind you of that as well, the interference patterns are what you get when two different waves overlap. Now, I say different waves, but the waves that are adding onto each other must be identical. They must have exactly the same wave speed, they must be the same type of wave, they must have the same wavelength. They can be in different phases though, and we talked about the idea of things that are in phase with each other adding up positively and creating constructive interference where the amplitudes will increase. And we talked about destructive interference where the waves are not in the same phase, they are out of phase, and that causes the amplitude to decrease. Here you can see a small animation in the top right corner which is showing the effect of constructive and destructive superposition. The top wave is not moving, it is stationary, and the second wave is moving to the right. But as it moves, it is alternating between being in phase and being out of phase. And you can see the resulting wave on the bottom, which is fluctuating between superposition, which is constructive, and superposition, which is destructive. So when the amplitude is increasing, that is constructive, and when it flatlines like that, that's destructive. The final task that we did last week was to look at this question, and we drew our own graphs, which were the sum of the blue wave and the red wave. We added them up at different points and we created our own wave, which shows the superposition of those two waves, obviously shown here by the yellow wave. Now, we've been talking about superposition of two waves at a time, and it's quite easy to think of it like that, and you can draw graphs to show and represent what you would expect. But if you use something called a diffraction grating, which is essentially lots of slits that will cause lots of diffraction, you will get very interesting interference patterns. And remember, if the interference is constructive or destructive, you'll get different results. So an increase in amplitude or a decrease in amplitude. These changes to amplitude create what we call an interference pattern. And the interference pattern will have the areas of high intensity and the areas of low intensity. Now, visually, we'll be doing this next week, and you'll be able to see the pattern produced. The areas of high intensity are spaced apart, so they're not constant. There is always a gap, and the gap between the areas of high intensity is linked to the wavelength of the light used and the space between the gratings, so the space between the holes. The relationship is n lambda equals d sine theta. Now, you do not need to know this equation in its entirety, but you do need to understand that n is the order of diffraction, and we have first order diffraction, second order diffraction, and third order diffraction. It's like having one rainbow, a second rainbow, and a third rainbow. The first rainbow will be the most intense, and the second rainbow, sometimes you can see that, and we call it a double rainbow. Now, there is actually a third rainbow, but you can't see it because it's so low intensity that it isn't visible to the human eye, but it would be there if we had a way of detecting it. So the order of diffraction is basically how many times is it diffracted, with 1 being the brightest, and then as it diffracts further out, there are increasing numbers of n, but they become less and less intense, they become less clear, until eventually you can no longer see the pattern. Now, like I said, with rainbows, you usually only see 1, sometimes you see 2, but you never see a third. And that's because by the third one, it's lost all of its intensity. Now, the phenomenon itself is actually useful, and you will probably have seen it. It's used in the entertainment industry quite commonly, and you can use gratings to split one wave into many waves. So The idea of laser arrays that are often used at parties is that a single laser beam will pass through a diffraction grating, and that diffraction grating will split that one beam into many beams, creating a very interesting effect. Now what you're looking at is actually an interference pattern, and you'll be able to find where n equals 1. And those will be the laser points on the wall that are the most intense. And as you go out from there, you will see that the intensity decreases on those laser spots. Now we can also split white light into its components, which I would imagine most students should have seen. So taking white light and you cause diffraction using a prism, you can split that white light into its component parts. In order to get these diffraction patterns, there needs to be a level of coherence. Now, coherence is just the word that we use when two waves are able to interfere with each other. So if two waves are coherent, they can interact with each other. They must be the same frequency and wavelength, but can have different displacements. So they can be out by different amounts of pi r. They have a different phase. This will apply to all types of waves, including light. So if you took two light waves from the same source, then you can have coherent light. They will interfere with each other and you'll get a pattern. However, if you get two different sources, two different lasers, and you basically shine them at each other, there's no pattern observed because those two lasers aren't coherent. They're not from the same source. So basically, if you cross the streams of those two lasers, nothing actually happens. This slide is a summary of the key terms for this section of the material. These are available on the VLE, so you do not need to record them now, although if you want to in your own time, then feel free, as it will be good revision. So we've got transmission, which is when energy is able to pass through an object, reflection, which is when something bounces, interference patterns we've been talking about a lot today, and coherency, coherent waves, just been talking about that. Superposition and path difference were from a previous topic, but this is a nice summary slide if you want to print it off yourself or just use it on the VLE. So to finish off the lesson, I've got some questions prepared which I've uploaded to the VLE, so you can find them in the physics section of the VLE just here. So superposition questions and superposition answers. Have a go at the questions and then check to see you've got them right towards the end of the lesson with the superposition answers. Okay, I'll see you guys tomorrow.